In Faraday's law, this flux psi is the flux through the surface whose perimeter is defined by the path of integration of E dot dl. In the videos demonstrating electromagnetic induction, we had a meter that was connected by two wires to a coil. We can model each component as a resistor. Let's assume the meter had a resistance of 1 ohm, each wire had a resistance of a half an ohm, and the coil had a resistance of 2 ohms. So we'd have this series circuit of our meter, wire through the coil, wire back to the meter. Let's increase the rate of change of the magnetic flux in the coil at a constant rate such that we generate a constant current of 1 amp around our circuit. With 1 amp flowing, I'm showing the resulting voltage drops across the 4 resistors. Let's sum the voltages around our circuit. Across the meter we have a drop of 1 volt. Across this wire, a drop of a half a volt. Across the coil, a drop of 2 volts. And across this bottom wire, a half a volt. So the sum of the voltages around our circuit is not 0, but it is 4 volts. Kirchhoff's voltage law is the special case of Faraday's law where there's no change in magnetic flux with respect to time in the circuit. Since n is the number of turns of our coil and is constant, we can move it inside the differentiation so that we have n times psi, which is just the flux linkage lambda. So we see it's actually the change in flux linkage with respect to time that is generating the electromotive force. If you recall when we talked about inductors, the inductance was the flux linkage over the current, not the flux over the current. This observation that it's the change in flux linkage with respect to time that generates the electromotive force is the experimental observation that will lead to our definition of inductance. To obtain this magnetic flux, we have to integrate B dot ds over this surface defined by our path of integration. We use a right-hand rule to interpret Faraday's law. So you put the fingers of your right hand in the direction of the integral of E dot dl. Then your right thumb points in the direction of the calculation of the change in flux linkage with respect to time. If the integral of E dot dl in the direction of your right fingers is positive, then the flux linkage in the direction of your right thumb will be decreasing with respect to time, so that dl dt is a negative quantity, so the right-hand side of this equation will also be positive. This will be much easier to comprehend after we work some examples. Now we have Faraday's law in integral form, one of our 4 Maxwell's equations. Notice that the n is not included when writing Faraday's law as one of the Maxwell's equations. You just have to remember that if you're dealing with a coil, that you have to insert the number of turns into the equation for Faraday's law. I've rewritten Faraday's law in integral form here. If the surface that you're integrating over is not changing with respect to time, we can move this partial with respect to time into the integrand. So on the right-hand side, it becomes minus the integral of the partial of b with respect to time dot ds. I am now going to use Stokes' theorem to rewrite this integration. Remember, we developed Stokes' theorem when we were talking about the concept of curl. So the integral of E dot dl around a closed path becomes the integral of the curl of E dot ds over the surface whose perimeter is defined by this path of integration of E dot dl. So we see that the curl of E must equal minus the partial of B with respect to time. And that's how we obtain the point form of Faraday's law. We will look at some examples which will help with the interpretation of Faraday's law and this minus sign. The correct interpretation of this minus sign is often stated as Lenz's law. The induced current is always in a direction to produce a magnetic field that opposes the change in magnetic flux that produced the induced current. Let's look at how to think of Lenz's law. So here we have a copper gasket and I have a magnet. So if I take the North Pole and move the magnet towards the copper gasket, there's an increase in magnetic flux into the page. So Lenz's law tells us a current will be induced such that a magnetic field will be produced to oppose this magnetic field into the page. So a current flowing counterclockwise around this copper gasket will produce a magnetic field coming out of the page, which will oppose the magnetic field increase from moving the north pole of this magnet towards the copper gasket. Okay. Now, if instead I take the magnet and move it away from the copper gasket, there is a decrease in magnetic flux inside the copper gasket. So now an induced current in the clockwise direction will occur to oppose that decrease in magnetic flux from moving the magnet away from the copper gasket.